In this lecture, we will continue with the lithography process. In particular, we are going to look at resist processing. In the earlier lecture, we discussed in detail about the pattern transfer and how this intermediate layer, when you are doing indirect pattern transfer, is very important. And one need to understand the property of this indirect pattern transfer, and also importantly the intermediate layer quality. So what is the purpose of this intermediate layer? Of course we know, but what are all the properties that we want this intermediate layer to possess in order to do the indirect pattern transfer? So in this first session of this resist processing, we are going to understand the properties of photoresist and also the dynamics of this photoresist. So optical lithography is what we are interested in, and if you look at the two generic way of taking an image, right? So that's what this lithography is all about. So the first left hand side image, you see this is just a camera, right? So the camera uses multiple lens arrangements, and then the lens arrangements allows an object that is placed in front of the camera to be imaged to this CCD, right? This is a solid state device. So this is how we do the imaging, right? And the object is far, so we say this as a far field imaging, right? Or in other words, it's a projection lithography. On the other side, you see near field imaging. This is similar to the puppetry that we have seen in this art works, right? So here the idea is you keep the image, right? So you keep the object very close to the screen, right? And if this is the screen, right? And your object is very close, right? And your light source is far away, right? So this is your light source, which is far away from your object, right? And then you have light coming through, and this distance between the screen and your object is very small. But on the other hand, here the object is far compared to the image that you have. I mean, if you have the right lens system, you're talking about imaging, some kilometer, right? Far images as well. So, since this is very close to the screen, almost touching, this technique is called contact lithography in technical terms. And since the object is far away, in the other technique, we call it as projection lithography. So in both the cases, the image is formed on the screen. So either the screen is here, or here the screen is placed here, right? So what is happening on the screen becomes very important. So this is how an optical system works, much more technical. Now you have a light source that is located as the first element, and then there is an illuminating optics. So this illuminating optics uses multiple lens systems, right? So the multiple lens systems allows you to profile the optical light source that is coming, and then you have a uniform light falling onto the mask, which is in contact with the wafer, right? So this is what the near field or contact image is all about. But if you just leave a gap, right? So if you just leave a gap, then this becomes a proximity printing or proximity lithography. So when you have both mask and wafer in contact, it is called contact lithography. When your wafer and your mask is separated by a gap, then it is called proximity printing or proximity lithography. And a completely more sophisticated technique here is you on the top, it looks exactly like the near field imaging, but the only difference is you have the illuminating optics on the top, and this is your mask, and then you have what is called projection optics, and then your wafer. So now the gap is very large, right? So the gap is very large, but not only large, but you have a dedicated optics. And this is what we call projection optics, right? In optical terms, this is Fraunhofer diffraction, and this is Fresnel diffraction, right? If it is a near field and far field. So in R&D and also in industry, we use a combination of these two processes. So this, irrespective of whether it is contact or proximity or projection, the image on the wafer, right, becomes very important. What happens on the wafer, right, is very important. So that is what we are going to see in this lecture. And on the wafer, we have a photoresist that is spin coated that we saw earlier, and then the mask is placed with a gap or on contact. It doesn't really matter. Here, for illustration purpose, we are just using a gap. And we are putting a uniform light source. So this is a light that is falling onto this mask, and we have transparent and opaque regions here. So in the opaque region, there is no light passing through. In the transparent region, we see light passing through. So when light passes through this mask and reaches this photoresist, something interesting happens. Depending on the type of photoresist, whether it is positive photoresist or negative photoresist, we'll see what this positive and negative mean. You will either remove the material or keep the material, right? So the exposed part is removed, then it is called positive resist. When the unexposed part is removed, it is called negative photoresist. But nonetheless, there is a photoreaction, whether it is reacting by solubility or insolubility. This is resulting in a photoreaction. So this is what we want to achieve. Solubility of the photoresist changes with exposed light, and that is the reason why this photoresist material should be photosensitive, right? It should be photosensitive, and it should not be photosensitive to all the light or all the wavelengths. It is very specific to a certain wavelength, right? So it should be very specific to a certain wavelength, and that is the reason why we say it should absorb only a particular wavelength, right? And undergo this chemical change that should result in solubility change, right? So this is what we want to achieve. And this lithography process is a lengthy process, right? Though we say lithography as a single unit process, it involves multiple steps. You start with wafer cleaning, which we saw earlier. So once you clean the wafer, you have to bake the wafer, because there will be some water or moisture present on the wafer. We need to bake it. What we mean by baking is just heating the wafer to remove the water from it, and then we will cool it down, and then after cooling it down, we will coat adhesion promoter, right? So when you are coating the photoresist, you want the photoresist to stick onto the substrate, right? If they don't stick, you will have some issues. We will see that what those issues are later, but you need to coat this adhesion promoter, and then we coat the photosensitive material, in this case resist, and then we'll do something called edge bead, right? So when you take a circular wafer, and then when you coat the material, of course you are going to coat it by spin coating, and then if I look at the cross section, so material will be coated, but at the edge it will curl, right? And this is what we call edge bead, right? It forms a bead right at the edge. So you don't want this, you want to remove it, right? So that is done by edge bead removal. And after edge bead removal, what we are going to do is we will use a baking step in order to remove the solvent present in the coated material, right? So there will be solvent, so we have to remove the solvent. So that's why we bake this material, to remove the solvent. And then after baking, we will also cool it down, because baking always happens at high temperature. We want to bring the wafer to room temperature, and once it is cooled down, you will now expose, right? Now you will illuminate it. After illumination, again you cool it down, because illumination will create some heat because light is absorbed. And then after cooling down, you also bake it. It's called post exposure bake, and then cool it down, and then after cooling it down, you develop. And this is an important step that dissolves whatever is exposed during your exposure step, right? And after developing, you rinse it, because this is a wet process. We remove that developer by using a wet process here, by using deionized water. It's a clean water. And then we again do dehydration bake, and then we cool it down, and then we take the wafer out. You see, all these steps are required, right? So if we have to name it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There are 15 steps, right? So you have 15 steps from the wafer going in, a clean wafer going in, and then you have a pattern. So the clean wafer will be something like this, and now you have a clean wafer with a pattern, right? So in order to achieve this, you need to go through all these 15 steps. So it is very important we follow all these steps very carefully, right? So that we get the result in a desirable fashion. So let's look at the light source that we use for illumination, right? So when you take this photosensitive material, and we illuminate this photosensitive material with a light source, right? And we are also clear about what kind of light source, right? So so you are sitting in a room which is illuminated by this tube light, for example. It's a white light, so it has all the wavelengths, right? So white light has all the wavelengths. So, but your photoresist material, as we mentioned, should be sensitive to only a particular wavelength. Why? Because if it is transparent to any wavelength, if you coat the material and then if you expose it to the atmosphere, because you don't do this in dark, right? There will be always some presence of light. So that illumination itself will bring in the chemical change. So you don't want that to happen. So that is the reason why you want to make this photoresist only responsive to a particular wavelength. Okay, so then you can restrict your environment so that the material is unexposed when you are taking it out. This is similar to the photo films in the olden days, where we used to have this cameras coated with photosensitive material, and all these developments happened in the dark room, because when the film is exposed to light, it will expose all the photochemical reaction will happen, and you will not form any image, right? The same technique is applied here, where you don't want to expose this photosensitive material to white light. So, or you don't want this photosensitive material to be responsive to all the wavelengths, very selective wavelengths. Right? So if there is a selective wavelength, we also want a source from that selective materials, and that is the reason why we are going to discuss about light sources. So this is the light source, particularly a mercury vapor lamp. So this is the spectrum of a mercury vapor lamp. If you take a very simple mercury vapor lamp, so this is an electrode, right? And then this is filled with mercury gas, right? So when you apply a voltage, there will be a arc created, and then there will be lights, photons coming out, right? And this photon will have different energy levels. And what you see here, it is the spectrum of your mercury vapor lamp. You can clearly see here peaks corresponding to the transition that you have in mercury, and also you see the peaks are not at the same intensity level. Some of them are very strong and some of them are very weak. So the 365 nanometer and 436 nanometer are very distinctive, 405 as well. So the 436 is called G line, right? And then 365 it's called I line, right? So this is signifying different emissions from this mercury lamp, and this 254, right? This is called deep UV. So 248 in particular is what we use, but this whole region is deep UV. So you also get deep ultraviolet emission from mercury vapor lamp. So now if you use a mercury vapor lamp, you will get this whole spectrum, right? So that is the reason why mercury vapor lamp, almost will look like a broadband white light source, because you have all the wavelengths here, right? So you go from blue to yellow wavelengths here, yellow to orange, right? So combination of all these wavelengths will make your vapor lamp look almost white, right? So as I mentioned, we don't want all these emissions, right? So we will restrict ourselves to particular region. So if I filter this eye line, we call it as a eye line light source, and if I can also filter out this 346 and use it. So these are all different regions one can use, and the light source, lamp light source cannot be used standalone, right? Because it emits all these wavelengths, and that is the reason you should always have a filter, so that you can filter out a particular region. For instance, if you have multiple peaks like this, right? And then the filter will have, it will be a band stop filter, right? A band pass filter. So where only it will allow this particular region to pass through. So the result will be only this particular region will come out. All the other light sources we are going to kill, right? So this is how we make this light source. And this mercury vapor lamp is used even in CMOS. Even today we use it for dimensions, below greater than 350 nanometers, right? So as I mentioned, back-end compatible process or metal lines or large features can be fabricated using this technology, right? So all the CDs that are pretty large can be used using this. So this should be greater, right? So so the next thing is how do we reduce the wavelength, right? So wavelength has a direct implication on the feature size, and if I want to reduce my wavelength, how do I do that? I use deep UV light source, right? In the previous slide, we saw mercury vapor lamps where the emission in deep UV is pretty small, right? Very small intensity. So we go to the halide-based excimer lasers, right? So argon fluoride or krypton fluoride gases are used to generate 248 nanometer or 193 nanometer deep UV light, and which is used for 90 nanometer or 650 nanometer technology. And right now we are using 193 nanometer for advanced CMOS technology. And this is all excimer lasers, right? And this is halide base, and you can choose your halide. Based on the halide you use, you can get the right wavelength. This is all about the energy levels, right? If you increase the energy level, you get a lower wavelength laser, right? So xenon fluoride lamps, it's around 342, right? And then if you go for argon fluoride, you're looking at 248 nanometer. Krypton fluoride and argon fluoride is 193, and then just fluorine based you can reduce it to 158 nanometer. So the choice of your halide dictates your wavelength, right? So unlike a simple light source, these excimer lasers are exotic. So exotic not just because we are using halides and gases, because the system itself becomes very interesting. You can see here, this is the light source that we have. It's not just a simple tube. It has water cooling that you can see here, and then you can see multiple cavities, right, that is all cooled, right, and then very active electronics that is sitting here, right, and this is the gas and then the pressure control chambers that you see here. So this becomes a very complex system, right, for one to use. The reason for that is that the transition itself is very important to control, right? So this is at the system level, so that you can appreciate why halide-based halide-based systems are much more interesting in terms of system engineering. So this is a mercury lamp. So you have a lamp source and then you have a mirror, right? As good as any illuminating system, and then you have a mirror that projects it to a filter. So this is the filter that you see here, and then this filter will choose whatever wavelength we are interested in. And then you have again another illuminating optics, which is trying to make a uniform distribution, right? So you have a light, a lamp sitting here, and within two mirrors, you get a very uniform illumination onto the wafer, right, and to the mask plate in this case. So the system is very simple optics. But if you look at the halide based or fluorine based system, it has a chamber. So this is a master oscillator and this is a power amplifier. So you have an external pump signal which goes through this master oscillator, and this master oscillator actually creates this particular pulse, or in this wavelength scale, that particular wavelength that you are interested in, and then it feeds into this power amplifier, right? So the power amplifier also has this, both the chambers do contain the fluorine based or whatever halide that you are using, but the only difference here is this is a very simple system where you take a very low energy photon and then you put it into this power amplifier, and this power amplifier has a cavity, so where the light will be bouncing back and forth, and this is what makes this system really highly energetic, and once it achieves the energy, the light is taken out, right? So why we need this master and power amplifier? The question here is this master oscillator always operates at low power so that you can have this wavelength stability, because wavelength stability is very important, so that your illumination wavelength is always kept at the same point, so that your resist can respond to that wavelength. So if you increase the temperature of this master oscillator, there will be oscillations in your wavelength. So you don't want that to happen, and that is the reason why your master oscillator is operated at low power, while your power amplifier is operated at high energies in order to use it for illumination. So that is about our light source. And next thing is the photoresist, right? So now we understand about the light source. So now let's come to the wafer side where we have the photoresist. So photoresist consists of three important elements. One is the base material, it's a polymer, a resin material, and then we need a photosensitive substance, which is called sensitizer, and then we add a solvent to make sure that this is in a liquid form so that you can spin coat it. So these are all the three constituents of a photoresist. And once you spin coat this, as I mentioned, we need to understand about absorption, right? How the light gets absorbed into this system. So a simple law that you can use to understand this absorption is this Lambert's law, where the absorption along the length is dictated by the absorption coefficient and the intensity that you have, right? So this absorption coefficient is per unit length. So you take a bulk of material, and then when you illuminate it with I naught, and after a distance z, you will get a power that is a resultant of this absorption after passing through this. And this gives you how the intensity profiles as a function of length, right? It is important to notice that this is a homogeneous medium, right? If you don't have a homogeneous medium, this alpha becomes a a function of length, right? So now this is not anymore. If it is inhomogeneous, then this equation will become something like this, right? So now since this alpha is from a homogeneous medium, it's almost a constant, so we don't have to worry about that, right? So this is how light is getting absorbed as it progresses through. In this case, light is absorbed from top down, right? So what makes this material absorb light is this complex refractive index that we have studied in our basic physics, right? So this is the real part of the refractive index, and this is the imaginary part. So the imaginary part actually contributes to your absorption, right? And also your absorption is a wavelength dependent factor, right? So it is important to understand that your material negative or your complex refractive index is very important to understand what is the extent of absorption at that particular wavelength. And this is all nicely explained by Beer's law, where the total absorption, right, in the medium depends on absorption of the individual constituents, right? So in our case, we had the resin, we had a photo sensitive material, and then we have solvent, right? So light is getting absorbed by all these three, right? The total absorption is a combination of all these individual absorption, and this is actually the ratio of individual absorption to the total absorption. This will tell us what is the individual contribution to this total absorption. Or in other way, one can look at this as the resin, synthesizer, solvent are all present. In this case, you will also have reaction products, right? So when you eliminate the sensitizer M, in this case using an UV source, you will get a product, right? And you also expect this product to absorb some light. So this is the total absorption that we are going to get, right? So the sensitizer absorption coefficient, and this is the amount of sensitizer present, and this is your product, right? So product will also absorb, and this is the amount of product that is sitting there, and this is the resin, right? This is the body polymer that we use, and the polymer would also absorb something. And finally the solvent, right? The solvent that we use to make your resist liquid will also absorb. So all these constituents is going to give you the total absorption, right? And the product absorption is pretty easy to measure, because your initial amount that is present, right? This is the sensitizer that was present, and synthesizer after eliminating with the source will reduce to some M, right? So this product is nothing but created by the difference in the amount of sensitizer present initially and final, right? And the absorption variation during exposure can also be given by using this relation. Your absorption is nothing but the bleaching parameter minus the non-bleaching one. So what is bleaching? Bleaching is nothing but while you are exposing, right, the sensitizer that you see here slowly starts to become transparent, right? So that is what happens. So if you take this as a photoresist, and then if you are illuminating with light source, the top layer is getting illuminated first, right? And then it will illuminate, it will get this energy, and then it will become transparent, so that light can penetrate through this material and then reach the bottom of this material, right? So as you go on illuminating, you will make the material transparent. So that is what we see here, right? The difference in the absorption coefficient to your concentration is nothing but the bleaching. So when it is completely exposed, this whole part, then we say the material is completely bleached, right? But this only happens for the material, the sensitizer M, right? But then the non-bleaching part, because your solvent, the resin, and the product, right? So that is generated, they don't change their absorption coefficient. Only the sensitizer changes its absorption coefficient. So that part is what we call non-bleaching. So the bleaching part and non-bleaching part will give you the total absorption change, right? And this is a differential, right? So the initial concentration and the final concentration, what is the change in the concentration of the sensitizer that I have. So ideally you want to convert all the sensitizer present in the bulk to absorb and then convert into product, and that is what you try to do while you are exposing, right? So what is happening when you are exposing? So when there is a absorption happening, you will have some heat generation, right? You will have some photon generation, and you will have some fluorescence, right? So there is some re-emission happening. There is something called photon assisted reaction. So some photocatalytic process could happen. This is also possible during this process. So the photon is not only used to change the solubility. The photon is also taken for other activities here as well. So you can imagine not all the photon is used for exposure, right? So there is a loss of photon to other processes that happens, right? So your absorption coefficient that happens is dominated by various fractions, right? So third order process, right? So you have the light speed that is dictating your absorption cross section, right, to your photon energy. So this dictates your absorption coefficient. If you have a low energy photon, your absorption is going to be high because the penetration depth is going to be low, so you can absorb quite a lot of photons in the bulk, right? So one need to think about what kind of energy that you are going to use and how the absorption cross section affects your lithography process. And this is an example of this resist process. In this case, I have taken Novolac resist. This is a phenol formaldehyde. This is a phenol resin-based resin. And when you illuminate with the light source, you will get some photoactive component, and then this photoactive component will make this material dissolve, right? So that is what we are trying to do. An insoluble sensitizer that you have in this resin becomes soluble, right? So this N2 group, right, is removed, and then this oxide, the exchange of this oxygen, right? So how do we achieve this sort of exchange process is what we are interested in, and this is what happens in the presence of exposure, right? You put in a photon. When you put in a photon, you can take out this nitrogen that leaves your dangling bond here, and then this dangling is going to be rearranged, right, in the presence of this oxygen and carbon in the bulk, and it will rearrange in this format, right, what you see here. So after rearranging, this is still insoluble, right? So you are only exposed and you have this material here. So what you need is water, right, or humidity in this case. This humidity will make this compound, right, soluble, right? This is if you take the COH group, and this COH group is soluble in base. So now you have made this insoluble sensitizer to a soluble product, and this is what you want to do when you expose, right? A very important thing to note here is just exposure will not help you to arrive at this soluble product. You need support of humidity, and that is very important parameter to control, right? So in any lithography process, you need a light source, and you also need to control the humidity. And the solubility factor can be classified into two, either positive or negative. So when you take a material, and then when you expose it, and then when you exposed part is removed, then we call it as a positive resist, and when the exposed part is kept and the unexposed part is removed, we call this as a negative resist. So here cross-linking happens So the backbone chain is strengthened so that they are not soluble. Here there is a dissolution inhibitor is created, so your solubility is increased, so you remove the material. So by using this either inhibition or cross-linking is going to make the material either positive or negative, right? And the next important thing is about amplification process. So far we saw one photon, right, will result in a delinking of a polymer chain, right? So you want to break this chain. So one photon breaks one chain, right? So this might be a quantum efficiency of 1, right? So this is what you are looking for. But this is pretty high ask, right, for any chemical process. So in order to have this process simplified, people use chemical amplification, right? So when you have very low number of photons, how do you achieve enough chain breakage? And people thought about this and they came up with this chemical amplification process. So the chemical amplification is nothing but one photon will generate multiple delinking, right? And that happens using this. So this is the solubility, and you take a simple resin and then we bake it. The solubility goes down, right? It goes down because you're removing the solvent, so it becomes hard, so your solubility goes down. But now when you expose it with your photon and you also had some energy, this is post exposure bake, right? So if you do post exposure bake, you also add some energy to this, and then the solubility increases. And this is what chemical amplification process does, right? Let's understand what this chemical amplification does. So the photosensitive material, right, it undergoes chemical change, right? That we all understand. But the important thing is, in a standard process, one photon delinks one chain, right? But in a chemical amplification, one photon alters many chemical reaction, and this is what makes this process much more efficient. So typically it can delink about 100 to 1000 number of chains, right? So this is what this chemical amplification is all about. So you don't need a lot of photons, so you need less energy elimination, so that you can delink a lot of this. So I would like to leave you with this final image, so that you can think about why all the lithography looms, right? This is Intel manufacturing unit, right? And then this is nanoscience fab at IISc. These are all the two lithography tools. One is electron beam lithography and the other one is optical lithography. You can see all these rooms are yellow in color, right? So why this is in yellow in color? Think about it, and then we'll discuss this details in the next lecture. So with this lecture, we are now understanding how this resist process works, what is the property of resist, and how elimination helps in changing the solubility, which is very important factor, right? And it can be positive or it can be negative. And also we saw how this amplification is again adding an additional dimension in handling this solubility, and also the power that you need in order to create this solubility, right? So with this, we more or less understand the photoresist. In the next lecture, we will understand more about the kinetics involved in this photoresist.